Yeah, so hi all. I'm starting a video series. It will be mostly around machine learning. It will be around machine learning. And right now, I will be focusing mainly on large model site. But yeah, and also like mostly I will be reviewing latest or some good papers. Okay, so now without wasting much time, let's dive into our first paper. Uh, right. So let me share my screen. Yeah. So this paper was recently released by folks in Huggingface, and it's called Building and Better Understanding Vision Language Models, Insight and Future Directions. Right. So they will be talking about practices like training as well as evaluation involving large multimodal models. And in this paper, they'll mention a lot of current practices, good practices, and what could be the area of improvements. With this paper, they have also released IDFix 3. So they'll also talk about like the entire methodology of creating IDFix 3. Apart from that, they also released Docmatics, which is a data set mainly that is intended to improve the document understanding capabilities. And the size of this data set is 240 times larger than like currently available data sets. So it's a huge data set, and it will it is supposed to, and it is actually I've seen it. So it will help a lot in improving the document understanding task using LMMs. Okay. So now, like, why this paper, right? So, like I mentioned, they will be mostly talking about current practices and the gaps or the area of improvements that they feel uh, is possible, right? During model training, evaluation, etc. So, what are the? I mean, why? Okay. So, if you see, right, even though there has been a lot of advancement in this LLM fields as well as visual language side as well, like which are called LMM. But still, like we see that the very fundamental things uh, like how do we merge the image token and the text token? Even there isn't consensus established yet. Like some of them just concatenate image token and text token, whereas other interleave it, right? So yeah. So for example, if you see like in Llama 3V model, they interleave it, whereas in other models they concatenate it directly, right? So why there isn't a consensus yet in this thing, right? What is the reason that still people are following different things? So they'll say in a similar way, they'll on multiple stages they'll talk about it. So let's just dive into it, right? Acha, okay, one more thing, the focus will be the architectures used to connect pre-trained language model with vision encoder. Basically, the connector layer, because just to touch upon like what LMM are. So LM means large multimodal model, right? So basically, on input side, there could be multiple modalities, as well as on output side, there could be multiple modalities. For example, the model might take input an image as well as a text, and it might give a output just text, right? So these are called multimodal model. Okay. So what are large multimodal model? Basically, those vision language model which has a large language model for its language processing, right? So they'll talk about like different architectures used to connect pre-trained language model with vision encoder, right? Different type of data involved in the training, different stages, etc. So training method as well as evaluation. Okay. Now, this section is around like analyzing architectural choices in vision language models. So first is like connecting uni model, pre-trained model. Okay. So most of the VLMs or vision language models, what they do is they just use a pre-trained vision model for vision encoding and a pre-trained LLM, right? Because they themselves are extensively trained, and and they just what they do, they take like I mentioned a pre-trained uh, vision encoder and a pre-trained LLM, and then they train a connector layer basically so that the vision token and the language tokens are aligned. So they just train a small layer or a connector layer, right? So this is usually what's done. Okay. Why not training from scratch? Because it will be too expensive to train, right? Because like there will be huge parameters in LLMs, and to train from scratch it's itself a challenge. So these two pre-trained models are usually connected either with a cross attention or a self attention architecture. Okay, so now here comes two design choices. Okay, like this connector layer, how does it work? So in cross attention layer, what will happen is if you see, so let me annotate it, right? So there will be a vision encoder. Okay, the input will come, an image will be a input. There will be a text, which could be some prompt. Okay, this will generate the vision embeddings. Okay, this will generate the text tokens. Okay, now what in cross attention architecture, what will happen is like the key vector and the value vector will be from vision side, and the query vector will be from text side. Okay, and in practice they say that cross attention block is inserted after every four transformer blocks in LLM. So which roughly it will be like one-fourth of the LLM size, right? So we are adding lot of parameters here while by training like KQV on these weight matrices, right? So what okay, so before that, like what this cross attention will do is like while this way what we can do is see these text tokens, they will attend to vision tokens. Like we'll have a query vector, and for every vision tokens, we'll multiply with the key vectors and like calculate an attention score across the vision token. So basically, we'll have a matrix across text cross vision. So how much a text token is attending to the vision token, that kind of architecture. So that's the cross attention architecture, right? And the thing to notice is that we are actually adding a lot of parameters, And so this significant increase in parameter enhance the model's expressibility, allowing it to achieve strong performance without unfreezing the LLM during training. So this is also a vital information that they are not freezing, they are not unfreezing LLM. Okay, so they are just adding new parameters and they will be trained. So the inherent behavior of LLM will be retained, and the model will be expressive as well. So these are some of the approaches which are using some of the models that use this approach, like IDFX1, OpenFlamingo, Llama 3B. This Llama 3B was also recently released. The other design choice is self-attention architecture. Okay. In here, what will happen is, yeah, I shouldn't have erased that. Let's see. Here, what will happen is like we will get the vision tokens. Okay. And we will get the text tokens and we just concatenate them. I mean, this could be concatenation or this could be interleave, like we have these are the text tokens and these are the image tokens. Okay, either of the way. So like initially vision token was contributing to key and values, but here a single, I mean, they will be concatenated and then self-attention will be calculated. Like each of them will have key QV and the attention metrics will have like all these tokens, right? So each of the tokens will be attending to each other, like text and vision. This is the second design choice, okay, for the connector. Now, the number of tokens will be less than the previous one, cross attention, because here we are like there we were adding after every 4 blocks we were adding this cross attention block, right? But here it's not the case. So the models like Lava, CoinVL, and DeepSeek, and Villa, Spin. So all this mini CPM, Monkey, MM1, InternLM, InternVL, these are pretty famous models and are good performing models. All these are using this design, right? Self-attention architecture. So this is the self-attention architecture. Basically, vision encoder, text. We get the there is like the hidden states vision encoder model, and there is pooling and modality projection, and basically these you can call like these are the finally the vision tokens, and vision tokens are then interleaved over here with the text tokens. They are passed to LLMs, and then we get the final text tokens. So now the question like which architecture performs best? So right, so let's go to other one more paper. Right. Wait. So this paper was also released by folks in Huggingface in this came around in May, right? And this with this they released IDFX 2, what matters with when we are building vision language models. Okay. Now there were some pointers that are pretty interesting. There are some learnings, some findings. Okay. So let's quickly walk through them. So the first question they ask is, are all pre-trained backbones equivalent for VLMs? Okay, so what are pre-trained backbones? Pre-trained backbones means the pre-trained uni models that we use, like vision encoder and the LLM. So like you see, the start from pre-trained uni model, how does vision and text influence the performance? Okay. So what they do is they fix the size of written backbones and model like that. They also fix the data, and under cross attention architecture, wait, let me change this to this. They observe the greatest improvement in performance on vision language benchmarks when they change the language model to a better one. So basically, so Llama 1 and Mistral 7B. So initially they took for language backbone, they took Llama 1 7B. And what they observe is if they fix everything, right? So the biggest improvement they see is when they improve the LLM. Okay. So for a fixed number of parameters, the quality of language model backbone has higher impact on the performance of the final VLM than the quality of vision backbone. So they are saying if you want to, I mean, the impact of improving the LLM backbone is much higher than improving the vision backbone. Okay, that makes sense as well because the main reasoning is happening in the LLM part, right? And after this experiment, it also shows that whatever information we are getting of the image, right? The image tokens that we are getting, it's sufficient to contain it as long as the LLM is able to process it. So that's the first pointer. Now, the second question they ask is how does fully auto-regressive architecture compare to cross-attention architecture? Like this is what we were discussing in the in our current paper. Okay, so auto-regressive architecture would be like the one with the self-attention, and cross-attention would be like what we discussed. So what they observe is the cross-attention architecture performs better than fully auto-regressive when unimodal are kept frozen. So okay, so that time, however, when training the unimodal algorithm fully outperforms a cross-attention one, even though the latter is more performant. So what they are saying is if we keep the unimodals frozen, like the vision part and the language part, the LLM part, if they are kept frozen, then we see that the cross attention architecture performs better. But if we do a full training of both the architecture, then we see that the self attention architecture, the fully auto regressive architecture outperforms the cross attention. The one more finding is unfreezing the pre-trained backbones under fully auto regressive architecture can lead to training divergence. Leveraging LoRa still adds expressivity to training and stabilizes. Okay, so this is also like over here what the point they are trying to make is like and what we have seen in LLM trainings as well, the concept of catastrophic forgetting. So they are saying that if we unfreeze the pre-trained backbone under fully autonomous architecture, it can lead to training divergence, right? So like if we train using the adapter based techniques like LoRa, so it is much more stable compared to fully training. That might be because of catastrophic forgetting or I'm see again like this is their finding, but what my opinion is like it also depends a lot on the training stage and the training data that is used, right? So we have to be very careful while fully training when we unfreeze the pre-trained weights. But anyways, like these are the learnings, right? So finding two and three kind of look on of like on from high level it looks like it's kind of contradicting, but again that like the takeaways are that uh like if the pre-trained, if the backbones are frozen, and cross attention is much better than auto regressive. But if we fully fine tune it, then auto regressive is outperforming cross attention. Okay, one more point. Even though cross attention will have more parameters, right? Because we have seen that one of the practices to after every four uh, transformer block to add a cross attention module. So these were the 2 points. There are more questions like efficiency gains and trade computer performance. Okay, I think that's fine. Let's move back. Right. So here, which performs best? So here they mention the paper that we are the author demonstrated that cross area significantly outperforms when the backbone are kept frozen during training. Right. However, when the part of vision encoder and language models are trained with LoRa, adding extra 20 million parameters across both model performs worse despite having more parameter overall. So this is what we discussed right now. So basically, yeah, I mean just 200 million parameters adding across in the both the architecture like cross attention as well as fully auto-regressive. The performance of fully auto-regressive outperforms uh, cross attention. Right now, impact of pre-trained backbones on performance. Yeah, so this also we just saw, right, that the LLM impacts more the performance than the vision part, right? Now this is very interesting. Is a vision encoder really necessary? So now again, like to quickly recap, right, how to do this, right? So what is an LMM? We have a vision encoder, okay, and we have a connector. Connector is basically what aligns the vision and the language part. And then we have a big large language model, right? LLM. So here comes the image, here comes the text, right? And we the strategies that we have seen, it could like there will be connector and these tokens will be then fed to LLM, which in turn will generate. Okay, white will not be visible here. So which in turn will generate the tokens. Right. So is a vision encoder really necessary? So the question is, do we really need this part? Okay, so let's read what they are saying. Okay. So instead of employing vision encoder, feeds image patches directly into language model after applying a simple linear projection to adjust the dimension. Okay. So there are two main advantages. It is independent of uh, another pre-trained model and preserves all the information from the original image. Just a second. Yeah, right. So what? So now, like, let's get back. So is a vision encoder really necessary? So what they are saying is that instead of having a vision encoder, why don't we directly feed the image patches, right, to the language model? And they're saying like you can use some simple linear projection layer to adjust the dimensions. So there will be two main advantages. One is it will be independent of another pre-trained model. Basically, the dependency from the vision is gone and preserves all the information from the original image. Yeah. So because we are directly feeding the image, so whatever in the vision encoder, some there, if some information is lost, then that will be preserved, right? Because see, usually there are splits, there are crops when passing through the vision encoder. There is some, there could be some information loss. Then encoding itself, some information might be lost than the original images, right? The latter point is crucial since the original image details might be necessary for accurately responding to the prompt. So there will be a prompt associated, right? We are passing a text with the image. So what they are saying is that the complete information of the image might be necessary if we want to respond accurately to the prompt, right? If you, right. A pretend vision encoder transforms an image into a representation that is independent of a user's prompt. So this is a very valid point. See, vision encoder is independent of this, right? So this is a vision encoder. And if you have seen, it is always independent of, just a second. Yeah, it's independent of the text, right? So when the encoding is happening, it has not seen the prompt, right? So it's encoding like on the basis of whatever it was pre-trained on, right? Whatever information it has beforehand. It's not dependent on the text prompt, right? So like just to simplify it, let's say we have an image of a cat, right? Okay, no point in drawing because it's hard. So let's say if we have an image of a cat and the cat is sitting on a table and there, somewhere in the background there is a clock, and let's say on that wall clock there is name of the company, okay, or there is some nuance over there, okay. So when it's encoding, it might retain like the encoded information, although like this is a very, I mean, simplified or um not it might not be accurate, but just to give you an idea, right? So the encoded information might have a lot of information about the cat, maybe about the table, right? Maybe about the wall and some the clock over there on the wall, right? But the information of like what's the name of the company, that that might be lost, right? Because that might not be attended, right? And let's say the text is what's the name of the clock, okay. So while encoding, it doesn't know that it has to attend to the clock a lot more, right? So this information is not with the vision encoder while it's doing that. So that's what the point is, right? That a pre-trained vision encoder transforms an image into a representation that is independent of user prompt. As a vision aim to compute as much information and can still miss the details pertinent to the prompt, right? Now, what we see here is Wish focus, okay, they are saying they attempted to address this drawback by incorporating users prompt to the vision encoder, okay. However, this approach is less natural in interleaved image text conversation where prompts may refer back to previous questions. Yeah, that's true. So in a chat like format, this is less natural because uh, you usually, give the image, give the prompt, then ask multiple questions, right? So every time passing the prompt with the image, there might be loss of the history. Despite disadvantages, this architecture not yet demonstrated superior performance. Polygamma, Polygamma is from Google. Let's check it. Right, Polygamma. Yeah, it's Google's model, right? Polygamma also experimented with this approach and reported a notable drop in performance compared to using pre-trained vision encoder. The author suggests that bypassing a vision encoder pre-trained on billions of images could lead to longer training times. Okay, so what they are saying that if we want to bypass the vision encoder, then the training time will significantly increase. You have to train a lot longer. That kind of makes sense because like the vision encoders themselves contain a lot of information, right? So yeah. Furthermore, handling image representation within language model might decrease its performance on text only branch benchmarks. Yeah, that also makes sense. So yeah. So one more interesting point they are making that even though this approach, even if this approach outperformed others multimodal, most VLMs are not evaluated on text only benchmark. Okay, so see in VLM we are using LLM, right? So LLM are language models. They're saying that if we directly start giving the image patches to the LLM, its parameters might change in a way that its outstanding performance on the text only benchmarks might decrease. And the one more point they're making that they are not extensively evaluated on text only benchmark of VLM. That's true. That's kind of fact. Model, it will be important to develop an architecture that can efficiently reduce number of visual tokens. Yeah, that's also true. Like finally, this approach has not been tested with efficient pooling strategy that does not significantly reduce information by operating directly on raw pixels. So yeah, so basically, so there will be a lot of image tokens. So they're saying that this hasn't yet been tested on efficient pooling strategy. So the like we'll have to looking ahead for tasks like video understanding or extension to other modalities. It will be important to develop an architecture that can efficiently reduce the number of visual tokens. Yeah. So see, passing raw visual token or the modality token can increase sequence length a lot, right? So there has to be done some study how we can effectively reduce the sequence length we are passing to the LLM. Otherwise, if the difference in the vision token, number of vision token and the number of text token, because text token would be just a prompt, right? If that's huge, then there could be some effect on the generation center. Okay, so this was his vision encoder really necessary. So current research looks like yes. How should we connect the vision encoder to the language model? Yeah, use again like this discussion is around the connector part. Right. So like what Lava does is it just use a linear layer between vision encoder and the LLM, and no pooling strategy is applied, right? So yeah, Lava is also pretty famous model, the LMM space. But training becomes less efficient as the sequence of visual token is too long, right? So what folks from QuenVL did is the right. So they introduced cross attention model between group of embeddings and hidden states. So yeah, so QuenVL paper is also there. Let's see. So the challenge is here is the cross attention that they are using, right? Where is it? Position of okay, here, right? The adapter part. So see, what's the challenge? The challenge is that if we in the connector, if we simply apply some linear layer and we don't do some kind of pooling, then the sequence length will be pretty high, right? Information will be retained, but the length would be, length would be uh, very long, right? So what would happen is the training would be very inefficient, right? So what folks from Quenville did was that to alleviate the efficiency issues arising from long image feature sequences, Quenville introduced vision language adapter that compresses the image feature. This adapter compresses single layer cross attention. We have already talked cross attention randomly. Okay, this module uses a group of trainable vectors as query vectors and the image features from the visual as the key for cross attention. Okay, so the query is coming from the module is a group of trainable vectors as query, and the image is coming from key. Wait, is query and the image from visual query. Okay, so vision is again like vision is giving the key, and this okay, and the finally the output would be of fixed length of 256. Right. The ablation of the additionally considering single potential information fine gain image compression 2D absolute position. Right. If you see the size, right, vision encoder is 1.9 billion. The adapter is just 0.08 billion and LLM is around 8 billion, right? So using the cross attention, they reduce the cross attention layer, they reduce the visual token size. IDFix 2 employs a cross attention model within a perceiver sampler. Okay, and so stat increasing number of visual tokens per image is primarily necessary for. Okay, so what they are saying is that we also need vision token if the task is very OCR specific. Yeah, that makes sense. Yeah. As far as the efficiency of perceiver sampler, its use has been challenged in several papers, which suggest leveraging the 2D structure here, which suggests leveraging the 2D structure of image more effectively. Since Honeybee introduces CF structure, yeah, which introduces 2B embeddings to the visual features. And Unplug All also had this as reducer, which uses convolutions to divide the number of image hidden states by 4. Yeah, so what these all are different kind of approaches, right? So the key point is in the like see ultimately the vision token and the text token are going into LLM, right? So what level of vision tokens are really necessary for the LLM to process? So what some are saying is that they just use a linear layer and all the information is retained. Some are doing some cross attention and creating a lower dimension vector. But they are also saying that the visual token might be necessary if the task is very OCR intensive. Okay, because that's true, because that becomes very challenging if lots of text is there. Right. So there are different strategies. I mean, there are different architectures again, right? And each of them would again require some in-depth discussion because a lot of things are discussed. Like perceiver sampler is mostly used in the artifix. Then this honeybee uses C abstractor and unplug owl uses as reducer. So that these are few techniques, right? Maybe in some other video I'll discuss about them in detail as well. Now we what all we have discussed, like quickly see, right? Impact of pre-trained backbones, like vision versus LLM. Is vision really necessary? Then the connector module. Now, now we'll discuss the image splitting strategy. So the vision encoder receives image, right? But let's see, right? Dividing an original image into multiple sub images. Each of each of which is encoded separately by the vision encoder. But why do we need to split the image? Right. Let's say what are different ways of image splitting. Like one is like we fix the crops, that like doesn't matter what's the resolution of images, but the number of crops or the number of divisions that image will have will be fixed. Other could be that we split after every n pixels. Okay. So let's say if the image is 1028 by 300, and let me draw it. So let's say if this is the image and if number of crops is fixed, so let's say if it's 4, then it will always be split in this manner. Okay. Whereas if the number of pixel is fixed, basically if split after every so and so pixel. So even though, let's say if this is the right image, so after every nth pixel, so it could be like this. So pixel size is fixed over here, right? So doesn't matter the resolution of the original image. Yeah, but the same image, if it has like the 4 as the crop size, it will be split in this way. When the number of tiles is based on the original resolution, the model is trained with varying number of visual tokens. This is an advantage during inference for similar tasks, visual needed, saving computational resources, while more computing can be allocated by increasing the image resolution for tasks that require intensive OCR. So what they are saying is when the number of tiles is based on the original resolution, the model is trained with varying number of visual tokens. Okay. This approach is particularly advantageous during inference. For simpler tasks, fewer visual tokens are needed. So, yeah, makes sense. So, let's say if the resolution is low, right? And if we have fixed the crop size to say, let's say 8. So, even though the resolution of the image is low, still there will be 8 image splits. And so each of them will be processed separately to the vision encoder. Right, but it's not necessary for simpler tasks, right? So if we use the pixel instead of crops, then for lower images, it could be processed in one go, right? Whereas the most complex one like the which require intensive OCR, they will have more splits, right? Because they'll have more pixels. So this makes sense. So model designed to excel both reasoning on a single image with high computational process. Yeah. Most vision encoder designed for relatively low fixed image resolution and are not well suited for processing large image. Okay. The image first addresses this by enabling the use of off-the-shelf pre-trained vision encoder at their original resolution simply by feeding multiple. You see, this is the need of image splitting, right? Since the vision encoder weights are shared across each subimage, this process also in a yeah, this makes sense. Like we do not need to have different weights for each of the crops, right? So training is also efficient. Okay, but there is one problem with this that uh, so there is an image, right? Image, each pixel of image also have some positional information with it, right? But when we split it, the context of a bigger image is lost, right? Because this split of the image are actually not independent of one another, right? So can we do something better? Okay, first to just to discuss. So some of the architectures, what they suggest is to pass a low resolution tile of the same splitted dimension, but this tile will be of the entire image. So downsized image, the entire image. So the model, the vision encoder will get a picture of the entire image as well to retain some of the global context. An alternative to the image splitting strategy and a promising direction is to develop a vision encoder that can natively process image of varying resolution, including very large ones, without changing the original aspect ratios, potentially implementing measures for handling text, long context efficiently. Yeah. Well, yeah, so basically there should be what they are saying, like whatever the challenge we discussed. So this will be got. Now comes the third section, training methods and data sets for VLM, like how to train a model, right? And what data sets to use. So I'll walk through this little quickly, right? So for pre-training, they're suggesting like multiple tasks and data sets that could be used, right? Stage one, stage two, stage three. So they are increasing the complexity or the resolution, the task, right? I mean, resolution of the image and complexity of the task slowly. And that's usually how we start, like the pre-training as well. Like some noise in the data is still fine in the very initial stage. So multi-stage pre-training. So the main goal is to align the backbone models, basically to train a connector, put it simply, right? This we have discussed already. Immunization typically kept low at start of the training and gradually increased over time, right? So why? Because so initially the model do not have to like, so initially the learning will be like the curve, the convergence will be low initially, right? So no point in keeping high resolution or more complex data in the initial stage of pre-training. Let the model understand the basic structures first. Right? Let it converge on a low resolution or simpler task, then gradually increase it. So these are few of the tasks and the relevant data set that they are mentioned in the paper. So there's nothing right to be discussed here as such, but it's a good source of information. PDF documents, synthetic data, image captioning data, then real world visual question answer BQA, text reading as well, text transcription, document understanding like the doc that they have released. That's really good, right? So this now coming to fine tuning and alignment, right? So fine tuning is usually, let's see what they have to say here. So alignment phase is basically preference alignment, okay? And fine tuning is like they are often anotated by humans, ensuring like high quality data, right? When we do silver, even though the size would be less, but it should be of high quality. You see, they are relatively small individually. When combined, they provide sufficient number of example effective fine tuning. Instead, we are among the first introduced curated mixture of academic data for fine tuning VLMs, building on the efforts. Yeah, the Quadron is also pretty huge and good data sets. Collection of 50 high quality data sets covering broad tasks, including general visual question answer. But here are the different tasks. Okay. So this could be used. However, drawback of academic data sets is their answer tend to be concise, which may lead to model generate similar brief responses, which are often less preferred by the users. Yeah, so one way is to rephrase using some LLM. Alignment is basically preference alignment training, right? So the model becomes more aligned with the human preferences. This also reduce hallucination. We chose, yeah. Again, like there are some more papers mentioned here. Okay, so now here they mentioned like what are the challenges in evaluating the vision language models. Okay, so first is open-ended and multiple choice benchmark. So earlier more such as VQA, V2, okay, and COCO captioning are mainly open-ended, rely on specific ground truth answer for each question. So even minor model responses can lead to score margin. This is very true. Yeah. So like any captioning task, right? Captioning could be artistic, right? It's not like we should do some one-to-one comparison. So is it fair to do the comparison on this, right? Writing style, yeah, see, tends to favor models that produce answer closely aligned with the benchmarks expected formal writing style. This is very true. Typically, short answers, right? Often just one word or two words. Even the evaluation prompt clearly specifies this format, right? This goes one potential way to mitigate this bias to perform few shots evaluation. Although this approach is less effective than training on benchmark training set and is not currently used in instruct models. The point is right. The current benchmark data sets they have their own formats, which could be unfair for some models. They are saying that to mitigate this, they could perform few short evaluation. What few short evaluation mean? I think could be like not sure. What do they mean by few short evaluation here? Uh, it could be that we give model choices to choose from, or it could be we ask model to generate multiple responses from which we choose. Basically, we do some few short evaluation, right? However, the level of ambiguity in this evaluation can, for instance, yeah, directly image replacing it essentially proposed lava metric consist of asking element. Yeah, this is this makes sense. So basically, they'll pass it to some other LLM and they'll ask like, uh, how is the response of the LLM, right? Compared to so some intelligent evaluation, not just some static metric, not just some basically syntactic metric, but some semantic. Yeah, yeah. See MCQ, what I was saying. So yeah. So what are challenges in model evaluation during pre-training stage? There is a significant additional performance. For instance, statistics to base score 59 text PQ using 8 in context example less than this during pre-training. However, after finding is okay in a zero shot setting without employing the image. Okay, as noted, these open-ended tasks are less influenced. Okay, so they are saying that once they fine-tune the model on these templates, right, the performance increased drastically. Specific of visual question answering. It says, unless a third pre-training stage is conducted, okay. When instruction data is omitted during pre-training, more complex like document may perform poorly. The impact of development choices in the VLM may only become evident after fine-tuning, leading to delayed feedback loop. Okay, this delay uh, instruction data even during pre-training can make pre-training ablations misleading, for example. Right. Cool, right. Makes sense. So what they're saying is that during pre-training stage, it's good to have some instruction data in the data mixture, right? So the model, so it's not like model does not have the reasoning capability, right? It does have, but it does not know. I mean, the it has not seen the instruction format, so it might not generate the responses that effectively to these specific tasks. So it's good to have this kind of data mixture. So the model knows, yeah, okay, so for this kind of questions means this, I have to generate in this way, right? Risk of contamination and over optimization. Some benchmarks, some data, some data. You found that 60% of the question include images from training sets or even often used in supervision. Yeah, right. Yeah, so they're saying that. So yeah, so what they are saying is don't train your model just to perform good on the benchmarks. Yeah, makes sense. I mean, there could be thing that if you basically include the distribution of the benchmark data sets in your training sample, of course your model will learn them and it will kind of overfit, not over if even if not overfit, but it will perform good on that data set. But that's not fair because that doesn't tell about the model's capability in general. Right. Now coming to IDFX 3, the new model that they released with this paper. So they'll talk about data preparation, extending the cauldron. Cauldron is the current data set that's already available, right? It contains all different things. What is this? Let's see. That's a data set used for fine tuning. Number of tokens is, yeah, this they have used for fine tuning, right? So if you see the distribution, capturing, OCR, documentation, and transcription. So this they use for fine tuning. Okay, the quadrant data set. Yeah, and they also released Docmatics dataset. This is like really good dataset, crazy dataset. High quality synthetic data for this task is relatively straightforward. If we reframe they're saying like they're talking about like creating synthetic data. That's OCR tools are intelligent enough, like good enough to generate extract text from PDF, and LLM can be used to QA pair, right? So the process they use for creating the Docmatics they have mentioned here, and yeah, they have discarded the low quality data as well from this. So this is filtered basically. Okay, now to show the importance or the capability of these data sets, what they did is they trained Florence 2 on doc VQA. Okay, and they on the train set of the doc VQA. Okay, doc VQA is again a standard data set. And so see, when they so on the same distribution, when they train it, the performance that they achieve using some like Florence 2 is 60.1. But if they train on dogmatics, right, it's a different distribution than dogmatic, then the performance is much higher. And even the right, this is Florence 2, this is much smaller than the IDFix 2. And if you see the Florence 2, the performance of Florence 2, it's just 3 or 4% lesser than the IDFix 2 generic model. Right, so this is an LMM, but Florence 2, the model size, if you see, is just 700 million. But just in introducing the dogmatics data set is improving its performance this much, right, compared to 8P. So it's really good data set, high quality data set. Now coming to architecture and training method. So yeah, it's similar to IDFix 2. They use Siglip and now they replace Mistral 7V with Llama 3.1 Instruct, which is much more newer model and much more, I mean, it's good model. So IDFix 2 uses Persever sampler to this into 64 visual token. They use Persever sampler, resampler, and IDFix 3 total too few tokens, right? So OCR capability has reduced because of lower visual token in IDFX 2. So uh, so to solve this, they replace the Persever sampler with a simple pixel shuffle strategy. This acts as a pooling technique that reduces the number of image hidden states by factor of 4, 169 visual token. During both, so basically this tends to improve the OCR performance, right? We follow image where the original is divided into tiles, like they are reducing, this is the tiles space, right? And the number of rows column matrix. This vision encoder processes each separately. However, because images and the number of rows common time is linearizing these visual token into single sequence can cause the model to lose information about original tiles. We follow common practice inserting text token after each row of tiles, depending on the scale. Okay. So see, increasing number of tiles, increasing number of splits will again like it will the model like the information of the entire document will be lost, right? So to tackle this, what they are doing is for each row they are passing the position, right? The X and Y, basically 0, 0, 0, 1, that kind of thing. And they also pass the original downsized image, right? And here, like they talk about like how they train it. First pre-training stage remains frozen. Basically, initially they just froze the uh, backbones, VLM and sorry, not VLM, the vision part and the LLM part. They froze it and they just did the pre-training on the low resolution images. Then they gradually increase it. And they use LoRa as well in the from second stage onward, right? So these are the three stages: learning rate, batch size. You see the max image resolution is increased gradually, then it's kept fixed. Backbones training like frozen, right? And the data, these are the data. So they use dogmatics here in stage 3, and fine tuning is done just on Cloud 1. Okay. So they are saying that they did not encounter instability when fully unfreezing the backbone, but they use LoRa for just training efficiency. It will be faster, right? But they are saying that if we carefully execute full unfreezing, it could lead to better performance. Yeah, it makes sense. Now, comparison of IDFX 3 to the previous version, right? So IDFX 3 8 billion. You see, compared to 70 billion model earlier, it's yeah, on MMU, triple MU, it's little low, but first of all, like with the 8 billion IDFX 2, it's better on all the benchmarks, and it's defeating like the on dock wiki is defeating the IDFX 2, right? These are on zero shot, right? So it's fair. So qualitative, so here are some examples there. So right, so it's good model, no doubt in that. Right. So overall, like what we saw in this paper was like all the different design practices and things like that we can focus on and the improvements. Right. We also saw I mean, even on the very, I mean, we even discussed like even if the vision encoder is actually necessary, right? So it's like its predecessor, right? The IDFix 2 paper was also on the similar lines with a lot of findings. So this paper also give a lot of, uh, it discusses a lot about like the LMM in general, the training strategies, the data. And we also saw the architecture of IDFix 3, the training strategies, training stages, and a very good data set was released, dogmatics, right? So yeah, so this was my very first video. So yeah, maybe I'll put this one pretty raw, but maybe going forward, we'll try to make more like aesthetically pleasing, like not using Zoom or anything. So put down your questions in the comments, and I plan to mostly do review our research paper and not on any fundamental topics. But if you have query about some fundamental topics, you just put it in the comment and I'll share the resources, because there are a lot of already lot of good videos across a lot of things, right? So yeah, thanks.